So, welcome back to the afternoon session. This is a completely improvised talk now. So, because there were several discussions, several references today to test data, and the question was, how do we get it? And I simply, on short notice, I suggested let's do a quick tutorial how you, even from here, could download your data. Because during several talks, like the M-Dwarf talk or the Cepheid talk today, during the talk I was downloading data and looking at the light curve. You can do the same. I would like to start at the beginning. What is TESS? I think, yeah, let's start. This is TESS. TESS stands for, if we have it, okay, TESS stands for Transiting Exoplanet Survey Satellite. It is a satellite that's pretty small. You could probably place the main bus on that table. It looked pretty small in the payload of the Falcon 9 because it was just small, and the telescopes are not too big. It has 4 telescopes of 10 centimeters. Why? Why would you build a multi-million-dollar mission and launch it and only put 4 small satellites, the telescopes up there? Suggestions. Why would you have small telescopes?
To observe brighter objects. To observe brighter objects.
Well, then you have even smaller telescopes and you call it bright. The reason for that is, with a small telescope, you can cover a large range on the sky. And this is what TESS is doing. This is the field of view covered by one telescope. That is about 24 degrees. And we all know that's about 10 degrees. So it's like 2 fists next to each other in one CCD. And you see not one field, but you see 4 of them. This is because of the let's see if we okay. This is because the 4 cameras are aligned to cover one strip which is about 90 degrees. It is aligned that one of the borders is just above or below the ecliptic to avoid the moon. The other, and you see, this is one, and TESS is in a luminescent orbit. In 27 days, it goes twice back and forth to the moon. It's a very stable orbit, which is, if you talk in binary terms, referred to as a cosine cycle that is stabilizing the satellite, and with the fuel on board, it could be operational for 300 years. So the joke for some time was ongoing, you can put your money on that TESS is still operational when James Webb will be flying, which had a couple of delays. You see those sectors here, this is only one, and it's turning around. Here, camera 4 is always pointing at the same region, which is referred to as the continuing viewing zone. So as long as TESS has one orientation, this field of view will always be observed on different positions on CCD, but it will be observed. So we can, the longest time series TESS can provide uninterruptedly is about 13 months. Here, if it's only observed in camera 1, it will be about 27.5 days with a gap in the middle, like for all sectors, which is when the satellite is flying by Earth on a very eccentric orbit, coming very close by, and telemetry is slowing down. The rate of telemetry is so high that NASA has increased the cadences with which they download the data. So with which they store the data on board have been decreased from initially 30 minutes to 10 minutes, and now I think with the next cycle it's 5 minutes. If
200 seconds. 200 seconds.
200 seconds even. So, Gerard, please come here. We do the completely improvised now. And invite everybody who's working with test data to chip in. You see, between the sectors, there is a gap. And if your target is in that gap, well, probably you will have to wait for a couple of years. The idea is to make a full panorama of the sky. Because there are several operation modi. This whole strip is stored. This is called a full frame image. The whole CCD is stacked on board to initially 30 minutes, then 10 minutes, and now 120 seconds, or 200 seconds, so, which is increasing. So each star in here that is brighter than, say, 15th magnitude has a light curve. So variable stars, this is now the threshold growth for variable stars. We find many of them, and we heard already a couple of times the aliasing problem. There is no day gap. This is a single-site continuous data for 13 days. Quick gap, another 13 days. So the frequency analysis is much easier than if you would do the same thing from the ground. The other way, and so this is made for exoplanets. This is why NASA is a big exoplanet mission operator. If you do variable stars, 30 minutes or 10 minutes are very likely be enough in time resolution. If you do exoplanets, you actually want a much higher cadence. And it would be too much for the satellite to take it, process it, and download it. It simply would be too much. However, what NASA is doing is, let's say this is our target. So they predefine a stamp around the target and read that one out and store it for every 2 minutes. And that is the high cadence. So we separate between low and long cadence and short cadence, and this data is sent down. What I will show you now is how you can retrieve long cadence data, because there's a bit more user interaction. Short cadence is only available for particular targets. And you need to get this data, there's a whole process involved that takes probably a year. You need to write a proposal arguing in 2 pages why either 1 or 1,000 targets. You make the deal. But you need to be convincing why NASA should put your targets on the prioritized list and not the others. And then once a year, people are meeting in a room like this, and the proposals are scrutinized. There's about 10 minutes discussion, and then it's roughly, it's a very, very straightforward process. And if you're successful, your like with the red nova dwarf flaring star, then it will be put on the target list and will be observed with 2 minutes. This data you don't access like this way. You simply would go to the MUST database, the Symposium Astrophysical Science Archive, MUST. And you can download the pre-processed and vetted light curve from there directly. Be aware, if you have longer time series, it might take a bit because it's a lot of data. Oops. By the way, that's also a spectrum of the sun. So how do you get? I think there are some images I wanted to show you. So if this is done for a couple of times, the first year was the southern hemisphere, second year was the northern hemisphere. So the satellite has done, in the meantime, 2 sweeps of both hemispheres. Those are the full frame images. That's one sector. Which object is it?
Fudge.
Hmm?
LMC?
The Magellanic Cloud. And I hope, okay, you see NASA is very focused on the, okay. If you want to know more, we can. So, how do you get the data now? And my neck is getting stiff. So if you want to, first thing, if you want to know if your target is observed, you can go to the web page, which is up there, and I can provide you the link. It's a web TESS viewing tool, WTV. And here you have several options. If you're just interested in one target, you enter your name here. This needs to be an official identifier. If you do, like the Cepheid Kevin was talking about this morning, is V1334 Cygni. Any identifier that can be resolved with SYMBOT. SYMBOT can also resolve coordinates in various functions. If you want more, like if you plan to check for 1,000 stars, what you do is you can create a CVS file, comma separate value file, and upload it. Or you simply can have cuts, where you say, I want to specify values in magnitude, color indices, you name it. So we stay with the Cepheid of Kevin Cepheid. I hit submit, and you see it takes a bit. Because right now, the web page is searching in Baltimore for the target and in the whole TESS catalog. Each of those bands we refer to as sectors. You see sector 1. Here you have from when to when the sector has been executed, and also in which cycle. Cycle is a proxy for, it's roughly a year. It's a year of operation. Cycle 1, and you know, cycle 1 is the southern hemisphere. Cycle 2 is from sector 14 is the northern hemisphere, and the nominal mission was 2 cycles long. So here it is. We see the Cepheid being observed in sector 15. We know from when to when it is observed. Now, TESS will continue. We don't know how long. Hopefully it could go on for decades, and we hope for it. So it will revisit that position again. And if we scroll down, currently the latest data is sector 50, which has been finished in April. And we already can download the data. At Lustbühl, Observatorium Lustbühl, we had a campaign on one RLI star to be simultaneously observed with TESS. The data is already there. Just to give you an idea on how quickly, what the turnaround of the data processing is inside TESS. And it's public. From the moment it hits the web, it's public. So you can drag it. But this web page also allows you to look into the future scheduled operations. It's not a guarantee, because sometimes NASA decides to change the pointing on short notice. For example, I had a whole campaign set up for one of my favorite red giants, which is called Gamma Pisci. And when I was searching for the test data, there was none. But when I proposed for the spectroscopy, it said what happened. They realized it was planned before launch, and NASA realized that the moon stray light is a bigger problem than they have anticipated. So they simply shifted the whole thing by 5 degrees. And if you have a target in the ecliptic, then it might be cut out. But in the meantime, operations are pretty straightforward and pretty stable. So here you can now look until the observations until sector 69, which is September 2023. So the coordinates are fixed, which is important for proposal cyclists. And this is fixed. What is not fixed is if short or long cadence data, but you basically can start planning your campaigns. And here we have, again, observations scheduled. Oops. Here, for the same Cepheid, we have observations scheduled in sector 55 and 56 from August 5 to September 30 this year. So you can use that tool to check when photometry will be obtained and schedule your campaigns of binaries of Cepheids.
Also, you know whether the second extended test mission has already been granted? Because I think so far, sure observations are only until the end of cycle 4, and cycle 5 is planned, but they don't have funded yet. Do you have any news on this?
Oh, no. That's new to me.
Should come any day now. So.
Any day now, okay.
I'm saying this for a couple of weeks. But.
Okay, thank you. So, see, this is also new information to me. Yeah, it's within the extended mission, so the funding was for the first 2 years. And now NASA is re-evaluating the mission based on the success. But are we worried if NASA is giving the money for that? I think it's... Well, I will put money on that they continue giving money in. But yeah, so we know for sure that sector 55 will be observed. We hope that sector 56 will be observed as well. But no, I think it has already, the panel has already met for sector 5, cycle 5. So I'm pretty sure about it.
No, I mean the proposals have been accepted, but I do not think that NASA has given the fundings for years 5 to 7 yet, as far as I know, but I'm not sure.
Okay.
And I thought you would have some
no.
inside information.
So that's actually new to me what you're saying. So yeah, but coming to the observing planning, if you know that your target is observed, you don't need to wait until it's observed. You can start your observations before and after, and then just have the core campaign during the time when it's observed. Now you know when your target was observed, and as astronomer slang goes, if it was on silicon. How do you get it? There are several packages available to everybody. I will introduce one to you now that I'm using. There are several of them, and you're free to use them. This one is called Eleanor, which is, as you can see from the logo, a pipeline. And actually it's a pipeline from the test sectors to the light curve. And it's even animated. How cool is that? Eleanor is, if all the questions you have about Eleanor are hopefully answered in the paper by Adina Feinstein from 2000 and... No, there must be a new one. This was the first one. So it's written by a PhD student who has developed that web page, and this is an abstract. This is a conference. No, there's a newer one. Here, no, 19. Sorry. So this is from 2019. This is the paper, the instrument paper on the pipeline, which explains the terms and techniques used in the extraction. This is a simple Python, it's a Python package. So you need to download it, you need to install it, and then you can use it in your Python scripts or in your Jupyter notebooks. This is improvised, so I did not produce a Jupyter notebook, and my codes are simply not presentable. It's, you know, when people say document your code or know what it's doing, at some point you, yeah, well. Anyway, here's a quick tutorial how it works. So and that's the point. Eleanor has a very small window of certain packages with SciPy, Matplotlib, and NumPy it requires. So that is something to find out, or I can provide you with information. So you need to install exactly them. Otherwise it's not working. So then, in your code Jupyter Notebook, you simply import Eleanor and NumPy, and that's the basic you need. If you want to be fancy, you import AstroPy, units, and coordinates, but that's already more than you need. Eleanor will also take care of the incoming sectors. So when you installed it at a certain point and you want to update it to, you know there's a new sector coming, or you want to check if new sectors are coming in, you can define update, and you define a number, and it will download all the metadata for that sector. It will also print a message which is the latest sector available. Then fast light curves, yeah. So you need to know, so Eleanor will also do the trick for you to check if data is there. So it's an object-oriented package. You send a request from your script, and this is the simplest version. You specify the tick number, and tick is the TESS input catalog. You have kick for Kepler and APIC for K2. And I take a wild guess that it probably would be PIC for the Plato input catalog. So this will, in that case, we already know that there's a sector, but later on there's an example where you simply cure for a certain tick number, and you create an object with the metadata that is required by Eleanor to search for your data. Yeah. So here you also can define a name and use a different specifier. And this star, you can give whatever name you want. This contains the information, and you can also write it out with star tick, that's the tick number, the Gaia number, the test magnitude, the coordinates. So you have a lot of information in the header. And I scroll down. You also can define. So what it's doing is it's downloading. So you have the full frame. And with this, now you say, so you created this object star with all the metadata, and in the next step, you tell Eleanor, go with target data, go search for that target. It has all the information, tick, coordinates, which sector. You go and download me a stamp, for example, 15 pixels times 15 pixels. And a pixel is about 1 arc minute, just for your reference. They're huge, they're giant, and it's introducing quite some problems. Also, background, I'm not fully sure what is this doing. Then you already have some other things, and this command will go download the data the first time. The second time, it is searching locally on your computer, which is speeding up the process quite a bit. and it's extracting photometry. It will be doing a point spread function fitting in that case, which is very time consuming. It will check the metadata for PCA. PCA stands for Principal Component Analysis, which is a trending way, because you have a lot. Don't believe that data, because it comes from a satellite, is beautiful. There's a lot of noise in there. But it's easier than ground-based data. What PCA, for example, is doing is you have numerous reference stars on the chip. They are supposed to be constant. And principal component analysis, we would better ask a mathematician what it does, but it shows that it's multidimensional, but it distills the way of the trends. So you can have a proxy of what trends are in your data, and they can be subtracted from the data. That's, from my experience, from my targets, the data to choose. And you can have a simple correction where the background is calculated from your stamp and subtracted from the data. Now, here we have Eleanor target data, and we write it into the array or into the dictionary data. Dictionary means we can use keywords to extract the information from the arrays. And now we already have extracted the data. Now we can plot it. The case is WASP 100, which is an exoplanet host. And this is now typical Python. We open a figure of a certain size. Now we filter for only the good data. So quality flag 0. Let's assume that for a moment. And then we plot data.time with the keyword 0. And then we take raw flux, corrected flux, PCA flux, and point spread function flux, and plot that in a typical Python diagram. And you see an arbitrary offset just to separate them very well. You see black is the original data, and you see some trends in here. And you see also some, and corrected in that case has smoothed those jumps out. Here in the middle you have a gap of half a day. That's PCA, and this is the photometry when you do a point spread function fitting, which is supposed to be the best way, but with those people where we talked about, it's for some reason it's not working as you have trends in the that are simply not real. Probably because the pixels are so big that a star roughly is on 4 pixels distributed. So that's probably a problem fitting a PSF to it. And yeah, well, you see, here you have a planet. And you can check the background models, what has been subtracted. You can play with that, you can optimize it. Here you have the pixel data. So if you're really fancy, you can even do a differential photometry so all you want to do, you can do, because you have your data as FITS files locally stored. You can define different masks, because the apertures. Because exoplanet people prefer the best illuminated pixels. They have simply the best signal to noise. If you want to do variable stars, but the best illuminated pixels, they can actually move on the chip. And if you have a static mask, you might introduce additional trends. Now, what seismologists are doing is we define a larger aperture to simply be more robust over a long time, because also the satellite has some jitter. And with this, we get pretty good results. This is a Python code for exoplanets, but you can force it to have a larger aperture. And here you have the, you can combine it with the light curve package, which is another package to do that. And you also have multi-sector queries. Like in this case, there are 2 sectors at least. There you have your data. And it's pretty well documented. And if there are problems, then in worst case, you can write Adina with questions. Now, what does it look like? I was saying that I was, during the talks, looking at the light curve, because this is what we do. We just, if there's a star, we pull the light curve to have a look at it. And this is the Cepheid we were talking today, this morning. Production time, probably 10 seconds, which was mainly downloading the data. So this is my messy pipeline set up for a certain science case where I compare, this is the pixel, there's a star on the pixel data. I extract stamps of 31 times 31 pixels. And this is the light curve with pretty much in agreement, but you see here the gap between the first orbit and the second orbit, and there's something. So I would recommend trashing that, and I think you have to align it. The other target we were talking about was the M flaring dwarf star, which is this one. This is, as I mentioned, this is long cadence data, not the short cadence, but we still see here a couple of flares. And if you zoom in, then you actually see a sudden jump and a few data points declining. Problem is, this is long cadence data, the flares are actually shorter lived than half an hour often, so on this scale you only see the large scales, but if you have short cadence data, you will see them as well. One thing, the flux that comes out is instrumental. It's an ADU. So you need to deal with that. It's not magnitudes, so it's actually flipped. If the star gets brighter, your flux is getting brighter, not smaller. And it depends on the cadence, what it was integration time, on the pixel number. So you need to take care of that by normalizing. Solar-like stars are easily normalized by the median. Red giant, Aralira stars are much more difficult. But you need to find your way of how you normalize that. This is for my science case, and the whole thing is very efficient actually. And as last, I show a quick paper that I finished earlier this year, where I used the pipeline to search for oscillating stars in red giant binaries. There are not too many stars in binaries known. If we go to the diagram, to that one, the black dots are the published sample of well-constrained binaries in the plane of period versus eccentricity. And we need those targets for science. And normally we search in the light curve of photometry, of the satellites, to see if they have an eclipse or if they have tidal modulation. And therefore we put strong constraints on the inclination or the eccentricity. And that's why we find only 40 after 10 years. Now in this paper I took a different approach. I took the SV9 catalog, the catalog SV9, Spectroscopic Binaries, 9th edition, which contains 4,000 binaries, all across all stages. What it does not contain is an information on where in the Hertzsprung-Russell those targets are located. However, one can take the astrometric missions like Hipparcos on the right or Gaia on the left, take the distance, make a photometric calibration, take the color index, and define those are my red giants. And suddenly we are left with more than 1,000 candidates. all the tools needed for that are available as well. In the last 10 years, basically everything in astronomy is available and has a Python package. And most of it is located in AstroPy anyway. And for those candidates which are red giants, I simply used the pipeline I showed you to search more than 1,000 red giants in about 2 hours. Download the data, extract photometry, and what we are searching for is this. This is a power spectral density diagram with the frequency on the x-axis and the power spectral density, basically the amplitude squared divided by something, on the y-axis, shown in a log space. And we're searching for this signature here. That is the power excess of solar oscillations. That's granulation in here. So we know this is a red giant. In this case, blue is the Kepler satellite, data from the Kepler satellite, 4 years, long cadence, best thing so far. TESS is in red, shifted for better visibility. Yeah, well, we can agree there is something. This is the difference of the satellite size. And with this, doing that for a couple of hundred stars, we found 100 new red giant binaries with an oscillating component. This was the science case I developed this pipeline for. If you have questions, I can help you. And this was also the diagram Jaroslav and I were referring to when we discussed the distribution of red giant binaries. And with this, I finish my improvised presentation, and we can talk afterwards if you have any. If you have any questions now or later, we can talk.